In the last video, we looked at factors and multiples. Specifically, when we factored a number, we broke it down, and we kept breaking it down into numbers that multiplied up to the original number. But sometimes we couldn't break it any further. For example, the number 24 was used heavily, and we found that we could write 24 as 2 times 2 times 2 times 3. But we can't break the numbers down any further. Why is that? This is because 2 and 3 are known as prime numbers, very important numbers in all of mathematics. The definition of a prime number is a number greater than 1 that has no factors other than itself and 1. Now, you might wonder why we separate out 1 as being special, and there are reasons for that, but we're not going to discuss them now. The number has to be bigger than 1. So 1 itself isn't considered prime. It's also not prime, it's a thing called a unit. It is special, it is on its own, but all other integers, all of the positive integers, 2, 3, 4, 5, can be characterized as either prime or non-prime. Let's have a look at some primes. 2 is a prime number. We can't divide it by any other numbers except 2 and 1 to leave no remainder. 3 is a prime, we've already said. 4 is not prime because it can be factored as 2 times 2. 5 is prime, no other factors except 1 and 5. 6 is not prime. It has factors of 2 and 3. Interestingly enough, 2 is a very strange prime. 2 is the only even prime, which in some ways makes it the oddest of the primes. But any other even number has a factor of 2. So any other even number can't be prime because it can at least have one factor of 2. However, 2 has no other factors. So this is something we can definitely say about the primes. They are all odd integers except for 2. Now, how do you know if a number is prime? Well, the best way to do it is to figure out if the number has any factors. Can it be broken down into numbers other than itself and 1? So what I'm now going to do is go through the numbers 2 to 11 to see if we can figure out ways of knowing if 2 to 11 are factors of your number. So let's start with 2. How do we know if 2 is a factor of a number? Well, it's not 2 and it's even. Even numbers all have factors of 2. If your number ends in a 2, a 4, a 6, an 8, or a 0, don't forget the 0, and the number is above 2, we can guarantee that number isn't prime because it will have a factor of 2. 3. How do we know if a number is divisible by 3? Here's a cool tip. What you do is you take the digits of your number and add them up, and you'll generate a new number. And you add those digits up, and you keep doing that, until you're left with one number. If that number is divisible by 3, then the original number was divisible by 3. Now I can prove this, we can prove rigorously that this is true, but we haven't got time to go into that. But let's do an example. 312. You take the digits and you add them up. So 3 plus 1 plus 2 is 6. 6 is divisible by 3, so I claim that 312 is divisible by 3. And in fact, hopefully you can see pretty easily that 312 is 104 times 3. Now I didn't know that until I did the calculation. I didn't know what two factors made 312, but I could guarantee that at least one of them would be a 3. So how do we know if a number is divisible by 3? Add the digits until you get one number, and if this is divisible by 3, the original is divisible by 3. How do we know if a number is divisible by 4? If it's divisible by 4, then it's divisible by 2. So we don't have to worry. If the number is even, it's divisible by 2. So we don't really have to worry about division by 4. Division by 5. How do we know if a number is divisible by 5? Well, that's pretty easy. If it's divisible by 5, the number must end in a 5 or a 0. Again, an easy check. If your number finishes in a 5 or a 0 and it's above 5, it can't be prime. It must be composite. Composite being the opposite of prime. 6. How do we know if a number is divisible by 6? Well, if it's divisible by 6, it must be already divisible by 2 and 3. So again, we don't really need to check divisibility by 6. We just have to check it's divisible by 2 and 3. So is it even? And do the digits add up to a number divisible by 3. 7. 7 is a huge pain. If you want to know if a number is divisible by 7, get a calculator. There are ways, but they're all more complicated than just sitting there and just doing the division, in my opinion. 8. Again, one of those nice cases. If it's divisible by 8, it's divisible by 2. So that's all you need to check. Is the number even? 9. If the number is divisible by 9, it's divisible by 3. So again, we just have to check its divisibility by 3. Note, I won't know it's divisible by 9, but I'll know it's divisible by 3, and therefore it's not prime. And that's all I'm checking here. I'm not really checking if it's got a factor of 9, or in the previous case, a factor of 8. All I want to know is that it's not prime. 10. How do I know if 10 is a factor? It ends in a 0. Simple, beautiful, and easy. If your number is bigger than 10, ends in a 0, it's composite. Now, the last one, 11. This one's quite fun. This one's a bit more unusual to do. Not many people do this one. And it's like the 3. So in the case of the 3, all we do is we add up the digits and we see if that number is divisible by 3. In the case of the 11, you add and subtract the numbers consecutively. Not just all add them, add, subtract, add, subtract, add, subtract, until you get to the end of the number. And you keep doing that. Add, subtract, add, subtract, add, subtract. And if that final number is divisible by 11 or is 0, then the original number is as well. Let's do an example. 2,541. 2 minus 5 plus 4 minus 1. 2 plus 4 is 6, minus 5 minus 1, that's minus 6. So 6 minus 6 goes down to 0. So because of this check, 2 minus 5 plus 4 minus 1, because that adds up to 0, the original number is divisible by 0. So I can guarantee that it is not prime. Fantastic. Very unusual rule that most people don't know, but it gives you an ace in your pocket if you ever have to check something that is divisible by 11. Very cool little method. Based on all these rules, let's do a problem. Suppose I have the digits, the integers 120 to 130. And suppose I tell you there is exactly one prime number in there. Can you find it? How would you do it? Well, you could go through each number and try and find the factors and use your calculator, and that would take a long time. How can we use the rules we just learnt to quickly get rid of some factors that can't be prime? Well, the first thing we do is get rid of all even numbers. We can get rid of those because we know they have a factor of 2. So first off, 120 is even, 122, 124, 126, 128, 130. That leaves us with 121, 123, 125, 127, and 129. Now we check the 3 rule. Add up the digits. Does that equal a number that's divisible by 3? 1 plus 2 plus 1, 4, not divisible by 3, so we leave it alone. 1 plus 2 plus 3, 6. That's divisible by 3, so 1, 2, 3 will be divisible by 3. 1 plus 2 plus 5, that's 8, not divisible by 3, we leave it alone. 1 plus 2 plus 7, that's 10. 1 plus 0 is 1, not divisible by 3, we leave it alone. 1 plus 2 plus 9, 12. 1 plus 2 is 3, divisible by 3. 129 is divisible by 3. Again, note, I don't know what the other factor is, I just know it has a factor of 3. So now we are left with 121, 125, 127. Let's carry on. We've checked for 3. We've checked for 4 by checking if it's even. There's no other even numbers left, so none of them can be factors of 4. 5. Does it end in a 5 and a 0? Yes, 125 ends in a 5. We know that must have a factor of 5. Get rid of that. So now we're left with 121, 127. Very quickly, as you've seen, we've got rid of most of these numbers, and there's only 2 candidates left. And we know one of them must be a prime, because we're told that in the question. Could it be a multiple of 6? No, because it'd have to be even. Multiple of 7? Don't check 7. No one's got time for that. Could it be a multiple of 8? They're not even, certainly not a multiple of 8. Could it be a multiple of 9? They're not divisible by 3, can't be a multiple of 9. Not a multiple of 10, doesn't have a 0 on the end. Let's try the 11. We take the numbers when we add and subtract the digits consecutively. 1, minus 2 plus 1 equals 0. Since that's divisible by 11, 121 is divisible by 11. So we can get rid of that. That leaves us only one candidate, 127. Now I could check that being divisible by 11, but we've been told in the question that there is exactly one prime number. Since I only have one candidate left, 127 must be prime. Now, finding primes is hard. And in some ways that's good. Primes are very important. One of the things that they do in our modern lives is protect our data. Because multiplication is easy, but division is hard, big prime numbers are used to hide our details. Now we're not going to go into how this all works because it's very complicated, but it's a very important field of research that if we could divide numbers a lot easier than we can, all of our bank details would suddenly become very vulnerable. So let's be very thankful that prime numbers are hard to find. So how do we do it? Well, there are methods out there. Some that will not necessarily always work, some that will give us a statistical chance of a number that we find being prime. But the surest way of ensuring that we can find prime numbers is using a technique called the Sieve of Eratosthenes. Greek mathematician, simple way of doing it, but brilliant, will always work, and it's very algorithmic. You can program it in a computer to always generate higher and higher prime numbers. And that's what we're going to do now. The first thing we do is let's do it on the first 20 numbers. So we don't have to worry about 1 because 1 is neither prime nor composite. And what Eratosthenes noticed was that you pick the first number that hasn't been crossed off your list, and then you cross off every number thereafter, which is a multiple of it. Hopefully you can see how this works. If I'm crossing off a number that's a multiple, it can't be prime. And any number that's not crossed off must be what's left. It must have no factors from the earlier numbers, therefore it must be prime. So let's take an example. Let's circle 2 and cross out all the numbers that are multiple of 2. 4, 6, 8, 10, 12, 14, 16, 18, 20. We go to the next number on our list that isn't crossed off, 3, and we cross off all the multiples. 6 is already crossed off, so we don't have to worry about it. Then we cross off 9, 15, and that's all that's left that hasn't been crossed off from deleting the numbers that are even. We then go to the next number. 4's crossed off, so we don't use that, but we go to 5. 10's already crossed off, 15's already crossed off, 20's already crossed off, so we don't have to worry about crossing any more off. Go to the next number, 6, it's crossed off, we leave it alone. We go to the next, 7. 7 isn't crossed off, so we cross out all the multiples. 14's already gone. We go to the next one, 8, 9, 10, all crossed off. 11. 11 is the first number that's not crossed off, so 11 must be prime. There are no multiples in our list anymore because the next multiple of 11 is 22 and that's beyond our list. So all the numbers left in our list must be prime. So 13, 17 and 19 are all prime. And as I say, I've only gone up to 20, but there's no reason to limit yourself. You could go up to 30, 40, 50, 100, a million. You can program computers to do this forever because there are an infinite number of numbers and you can always generate the next prime number using this method. In this video, we've been looking at primes, introducing them as one of the most fundamental, beautiful, amazing and incredible parts of mathematics. Huge amounts of mathematics is dedicated to understand how they work, how to find them, what do they do, what properties can we understand. We're going to use them in the next video to help us calculate the highest common factor and lowest common multiple without having to list all the factors.